Hi everyone, good afternoon. My name is Satyam Vagani. We'll get started. Thanks for staying out late. We hope to make this worthwhile. The usual disclaimer. Now today we are going to talk about vStorage APIs for array integration. That's what Lucas, my colleague from VMware Alliances, is going to do. But I'm going to start off and I'll try to give you an overview of what vStorage APIs is and why we did them. And then I'm going to come back later to talk about some future projects that we are doing in this domain. I'm an engineer. I created vStorage APIs, and some of you know me from my past work on VMFS too. So I had a hard time trying to narrow down the scope of vStorage APIs into one sentence definition. So I'm going to try an analogy instead. And the analogy is that around a decade ago, VMware created virtual machines, and the problem we were trying to solve was create these containers which are isolated from each other, and then run them on CPUs which are actually not capable of running these containers in an isolated manner. And so to solve that problem, we had to create this special piece of software. It was called a virtual machine monitor. That's been our crown jewel all these years. And we employed some techniques like binary translation and direct execution to actually get the isolation on a piece of hardware that wasn't capable of giving it. But then over the years, what happened is the hardware vendors baked in some virtualization features in hardware. Intel came up with VT, AMD came up with V, some core virtualization features. There were memory virtualization features, nested page tables and extended page tables, which let us change the way we virtualize machines. We made a hardware-assisted virtual machine monitor. Now, obviously, this was much more performant, scalable, because it was assisted by real hardware. And the other side effect, obviously, of doing this is the boundary between where virtualization starts and where it ends blurred. Now, that was great because that was the first time virtual machines were actually run as a first-class entity on a computing system. Now, we did something similar for virtual machine storage, as we believed that there was a much better way of doing virtual machine storage, much more scalable, usable, manageable way of doing storage than just attaching virtual machines to raw devices. And so we invented this concept of virtual disks, which are some sort of files or a combination of files. And then we had to invent a whole ecosystem of storage solutions around that new object. And so we had VMFS, we have storage, vMotion, link clones, our own snapshotting technology, and so on. And then all this while, we've been treating the real hardware at an arm's length. We just treat it as a media that you can do reads and writes to. That's all. But then over the years, it was kind of obvious, but hardware has become really, really sophisticated. It has the amount of processing power, the cache, the algorithms to actually add some value to virtual machines. And so the next step in this evolution is to figure out how we can actually preserve the concept of virtual disks as VM objects, but offload a whole bunch of virtual disk related activity to hardware so it can be done in a much more efficient manner. And that's what vStorage APIs is. It actually makes that link between our virtualization layer and what exists in storage hardware. It could be SAN or NAS. Now that's a big picture, and this is how we go about doing things. On your right, you'll see ESX, which is the data path, so to speak. That's what virtual machines run on. And then there is an analogous data component from a storage vendor, which is the disk array or a NAS device. And both these systems have their own management buddies, and so we have vCenter and storage systems. Each of them have quite sophisticated management tools themselves. And so we publish a specification. We call it the vStorage API specification. We publish it to storage partners, and it defines certain primitives by which ESX can talk to a storage system, or our management entity can talk to their management entity at a meta level. We can express meta level things about what virtual machines want to do, as opposed to just data level things like reads and writes. And so now the storage entity gets a better understanding of what the application or the hypervisor is trying to do. And so then we make some changes on our side. For example, with the most recent product that we just released through vSphere 4.1, it's called vStorage API for Array Integration, VAI. we made changes in the VMFS driver to do hardware-assisted functions, and Lucas will go more into that, so I'll leave it at that. But there's a kernel module change, for example. There's a bunch of other kernel components that change, and similarly, there's a bunch of management objects that change to have new properties related to VAI. And then on the hardware vendor side, they need to make new firmware to accept the primitives that we are going to send them down. And there might be changes in their management domain as well. And we make a protocol. It could be SCSI changes or it could be NFS changes to link the two. And together, I would claim that now you can see this entity, these four things, as just this one seamless system, which will let you do virtual machine-based storage solutions in a way that wasn't possible earlier. Now, VAI is our most recent thing, and you must have obviously seen it in the booths and in the keynote. There's a lot of buzz around it, but I'd like to highlight the fact that it's not an isolated thing. We'd like to address all aspects of virtual machine storage, and so we have vStorage API programs for various aspects, ranging from data protection to disaster recovery to performance and scalability, which is what VAI is about. And there's a few more things coming down the pipe, which I'm going to talk about in a few more minutes. But before then, let me hand over to Lucas, who will talk about VAI.
All right, thank you very much, Satyam. And thank you for coming to this last session here. With vSphere 4.0 and older releases, for every I/O operations, I/Os are read from the source and write are executed to the target. So the source and the target here is the storage array. So with every VMware I/O operations, server CPU and memory resources are being consumed, in addition to placing a bandwidth load or usage on the physical ISL and SAN infrastructure. So with vSphere 4.1, we released something, a new API that allow for hardware offload operations. So this is the vStorage API for array integration, VAI. And as the name implies, array integration meant providing an opportunity for storage partners to provide hardware offload operations. And the result is that I/O operations are much more efficiently accomplished by the storage array firmware. And in addition, the other advantage is significantly less or no usage on the bandwidth ISLs. So what is VAI is simply a VM kernel API and a set of proprietary or proposed SCSI commands between ESX and the storage array. And you will need to upgrade the storage array firmware to have this new protocol support. As Satya mentioned, in vSphere 4.1, we introduced a new terminology, primitive, to describe a set of fundamental operations between ESX and the storage array. And the end result is basically an efficiency in I/O operations. And another result, the key advantage is increase in data transfer, which is transparent to the end users or customers. So with vSphere 4.1, we will support the following three primitives: full copy, block zeroing, and hardware-assisted locking, or using atomic test and set, or ATS. So full copy basically leverages the storage array to mass copy a snapshot, for example, a large number of blocks. Now, a single clone typically should be able to transfer between 1 megabyte to 256 megabyte. Now, typical transfer sizes are 1 to 8 megabyte. By default, ESX will have a default clone block size of 4 megabyte. In regards to alignment, ESX will align starting with a logical block number to 64 kilobyte. And so for transfer sizes, it will be in a multiple of 64 kilobyte. Block zero here refers to the existing T10 write same command, a 16-byte SCSI command that does the zeroing of a large number of blocks. And with write same command, it significantly reduces the number of total time to provision the virtual machine. And with the hardware offload operation of block zeroing, we are able to eliminate redundant write commands to the array, saving ESX server CPU and memory resources. Hardware-assisted locking using atomic test and set ATS is a new algorithm for locking. It is an alternative to the existing SCSI reservation that would normally lock out of the host from concurrent LUN access. And ATS protects the metadata and VMFS file, cluster file server, allowing for scaling of a larger ESX server environment for cloud computing. that you will see in the future. The key advantage of ATS is that it allows for scaling by modifying a sector on disk instead of using SCSI reservation, which will require locking of the host from LUN concurrent access. And ATS does this by locking now at the block level and not at the LUN level as in SCSI reservation. Let's take a look in further details how the three primitives work. A very simple example here, I have ESX server issuing SCSI commands in band to the NetApp filer. And a use case here, for example, I request to clone a number of blocks, let's say 10 blocks, for example. So ESX would have to issue a read at the first address, 0x00 Fox Charlie, the first block, for example, and then we'll have to write to 0x Fox Charlie, the first block, read the second block, write the second block, read the third block, write the third block, and so forth. So as you can get the idea, multiple read and writes until the number of block ranges requested is completed. Now with VAI full copy, ESX will only have to issue, same example of requesting to clone a number of blocks. ESX would now issue a single extended SCSI command to the array, and the array offload the operation, does the full copy at the array level. So as you can see here, much more efficiently done by the array. Hardware-assisted operations are much more efficient and faster to complete. And the use cases for a full copy here is that you can do VMDK template deployment for virtual machine deployment, reducing the time to provision a virtual machine. Snapshotting a VM is another use case example, or a VMDK migration using storage vMotion, for example. Let's take a look at how fast is fast. Here's a result submitted by EMC with a full copy showing on the left there without VAI full copy, and you can see the bandwidth utilization showing about 239 megabyte placed on ISLs. Now with VAI shown here, zero because the hardware operation is offloaded. The operation is offloaded to the array, and so there's no bandwidth placed on the ISLs. In the next example showing here is block zeroing without VAI. Traditionally, the use case example here, for example, is if I request to clone a eager 0 thick disk. And so in this case, ESX would have to issue the write to the first block, write to the second block, write to the third block, multiple write commands until the list of block range is completed. With VAI, with block zeroing, much more simple. ESX would have to issue a single write same command to the array, and the array would do all the initialization, zero all the range of the blocks being requested. As you can see again, hardware offload operations is much more efficient and faster to complete. And the use case for block zeroing is, as I mentioned, to request a clone for an eager 0 thick disk, to allocate new file blocks for a thin provision disk, for example, or initializing an previously unwritten 0 thick disk. Let's take a look at how VMFS locking works in vSphere 4.0 and older releases. Showing here a very simple example, 3 ESX servers sharing a common LUN. Normal I/O operation is observed with normal between ESX 2 and 3. At any given time, ESX server 1 would need to request for a power on to start a virtual machine. It does the read and acquire SCSI reservations, and it locks the LUN. Unlike ATS, it would have to block out other hosts from LUN concurrent access until it releases the reservation, and you can resume normal I/O. With VAI, hardware-assisted locking using atomic test and set ATS, similar scenario, you have 2 ESX server, normal I/O is observed. Server 1 wants to start a VM. It checks for the VMDK for locks. So ATS modifies a sector on disk without using SCSI reservation that would normally lock out other hosts, server 2 and 3, from concurrent LUN access. So blocking now is at the block level and not at the LUN level, as in SCSI reservation. So you can still have normal I/O operations. Now, wasn't all this work a significant improvement? So hats off to VMware and our storage partner engineering team. Now, how fast is fast? Let's take a look at another quantitative example from HP here. In the first test case, for example, to do a VMDK template deployment of a 40 gig disk, it is shown here as 7 times faster to copy and 94% less load with VAI. As shown here on the upper right graph, as you can see, it took about, without VAI, about 5 minutes to complete this operation. With VAI, it only took 47 seconds. Significant saving in time to provision a VM. And on the lower left there, on the load on SAN, significantly less I/O requests being observed with VAI. And on the lower right there, showing 0 for full copy with VAI. 0 because operation is offloaded to the array, so there's no bandwidth usage placed on the ISLs. And the second use case example here is to do a clone of a eager 0 thick disk of 256 gigabyte size. And again, here showing a tremendous amount, 21 times faster and 92% less load with VAI. On the upper right-hand graph there, you'll see with VAI, it is only 62 seconds as compared to about 20 minutes operation. From 20 minutes down to 62 seconds, a significant time improvement. Again, on the load on the SAN with block steering, significantly less I/O being requested. And again, there's no or 0 bandwidth usage placed on ISLs because the operation is offloaded to the array. During the 4.1 release timeframe, or previously before its release, we've been working with a number of our storage partners to provide a unique vendor SCSI commands. In the very near future, we will broaden the participation for partner to adopt a VAI. And currently, these are the storage partners listed in alphabetical order, to be fair, of the firmware release, target release, and the firmware version. Now, I was talking to someone, and I believe EMC have just released today the Flare 30 for the Clarion to support VAI. But please check with your storage vendor for the exact time frame and firmware version. Now, when we ship 4.1, VMFS driver now is a new version, 3.46. It is to support the primitives, and the on-disk version upgrade is not required, to note. You will also notice here from the configuration storage page, there's a new column at the end that reads hardware acceleration, and it shows the 3 states. The first state is not supported for next to an NFS type, and the reason being the 3 primitives are only supported for block SCSI and not yet on NFS. The second state that shown here is unknown. That's because the hardware acceleration primitives have not yet been attempted. However, if you upgrade your storage array firmware, it will change to a supported state. And another way to check is to issue in the remote CLI, for example, issue command ESXconfig SCSI device and give it the NAA unique identifier. And you'll notice at the bottom here shown VAI status to be shown as supported. So next I'd like to invite Sajim back up to discuss the future API, and he will give you a sneak preview.
Thanks, Lucas. So I'd like to just square out a few VAI things. Lucas did, obviously, he did an excellent job. Since I'm an engineer, there are a few things that kind of stand out to me, which probably might not be obvious. One is we've taken a lot of care to make sure this is a seamless migration. And so we are not actually trying to get you to change the way you've actually deployed storage or how you maintain storage. If you happen to upgrade to vSphere 4.1, and if you upgrade your disk arrays firmware in any order, VAI will kick in, and that's as easy as it can get. Now, I've talked to many storage administrators, and obviously there are concerns about upgrading disk array firmware because it also affects other applications other than VMware that run off of that disk array. And so out there, the thing I'd like to highlight is these primitives are extremely simple, although the use cases that they serve are extremely complex. So for example, now Lucas hopefully convinced you that we've hardware offloaded things like storage vMersion or virtual disk cloning or writing to a thin provision VMDK, among other things. But the primitives that actually go on the wire are as simple as zeroing a small part of the disk or copying from one part of a disk to another part of maybe another disk. And so that is what keeps all this tractable. That is what leads us to deliver these features over and over again in phases, without tremendously impacting maybe the reliability or the performance of whatever you've already deployed. There's also another side effect of keeping it simple is the number of storage partners who will be able to implement this is going to be tremendous. And so we expect most of our storage ecosystem, storage hardware vendors to come in and participate. You've already seen a list of 10, which gives us enough coverage. The other thing is, VAI is always seen as a great improvement in performance and scale, but that was not my motivation when I started designing it or when the engineering team started implementing it. The motivation is to shatter core assumptions that you made about how storage works and how you got to use it. And the reason we want to do it is because the private cloud is going to be much more dynamic, both in terms of CPU utilization, the way virtual machines move around, and also how virtual machines actually use storage. And so we'd like you to force you to rethink through VAI about how you can change your practices to actually get to that level of dynamism now that certain core operations are way cheaper than what existed a generation ago. And so that said, there's something we are doing with hardware thin provisioning now, and I'm going to call it vStorage API for thin provisioning. It's a new program. We are exploring it for the future. And you might realize that this has to do with hardware thin provision devices, but the goal is something bigger. The problem we are trying to address is that you tend to provision a lot of LUNs for ESX, and this provisioning activity is quite complex compared to other operating systems because ESX always operates in clusters, and so you have the problem of provisioning a LUN and then mapping it to every HBA, every port of every machine in the cluster, and doing it at the scale at which ESX requires storage, consumes storage, is a very difficult thing. And so we'd like to reduce the amount of provisioning that you do. And one way, at least we could come up with to address this problem, not to make it go away, is to go to a model or make you migrate to a model where LUNs are just these tremendously large address spaces. They are large bags where you can just throw VMs in. And as long as these are virtually provisioned or thin provisioned, you don't have to commit storage upfront for these large bags. You commit storage as you throw in more VMs or as the storage footprint of every VM expands. And so that is why thin provisioning is strategic. And we are going to do a few interesting things there. I do realize that going to large LUNs is not as simple as I just made it look like. There are many architectural problems which have prevented you, for example, from going to large LUNs. There are problems in ESX. For example, SCSI reservations would limit the scalability of how many VMs you could put on a VMFS volume. But you just saw that with hardware-assisted locking, that problem goes away. We've also given you VMFS volume growth such that you can actually keep on adding capacity to an existing VMFS volume as opposed to creating new LUNs and then mapping them and configuring multipathing policies and so on. Now, there's some more good news on the VMFS volume grow front because one obvious question is, well, I can only grow up to 2 terabytes. But there's good news there, and unfortunately it's beyond the scope of this presentation, so I'll just leave it at that. There were congestion problems in the fabric, but people have now moved on to 8 Gbps fiber or 10 gigi, and so those have been reasonably solved. Queuing problems in the switches have been reasonably solved. And then on the back-end part, vendors have come up with auto-tiered disk arrays. So you needn't look at a LAN as being one static quality of service entity. A LAN could be made of different storage tiers, such that all kinds of I/O bottlenecks could be solved by moving parts of LANs to different storage tiers instead of actually moving your entire workload from one LAN to another. And so at that point, it becomes feasible to actually have a conversation about making a LAN thin provisioned. And what we are going to achieve by doing that is we are going to separate the LAN, which is a presentation concept. That's the way the SCSI protocol wants to send I/O to a disk array. So that's a presentation concept. And then there's the more important thing, which is the space concept, is how much space the LAN actually consumes. And so I want to separate those two things, and thin provisioning allows us to do that. However, it has two unsolved problems. One is the space problem kind of comes back after a while because dead space accumulates on the LAN as you churn through data, and there's no way to currently get rid of that dead space. And the other problem is when things really go south, i.e. you run out of space, or when you're close to running out of space, it's just an operational nightmare. So we'd like to solve these two problems, and that's exactly what this new API set will do. So let's do the two problems one after the other. The first thing is dead space. And dead space here is defined as parts of the VMFS volume or the LAN that the VM previously wrote to, but now no longer is interested in reading from or even writing to. And one easy example why dead space happens to come around is because files are deleted. And so at that time, the file system knows to reclaim blocks. It'll just free out the blocks that were deleted. But there's no one to tell the disk array that the following blocks, which seem to contain valid data, are no longer used by the application. And so on the right, I'm showing a VM example, and we are going to use storage vMotion as an example. The virtual machine has stored its data on VMFS volume A, and the data could be a bunch of files, which are eventually a bunch of blocks on the VMFS volume, which I'm showing in green. Now, when you storage vMotion a VM, those blocks will migrate to volume B, but no one will tell volume A that the blocks in red are no longer used, and hence can be removed. Or let me rephrase, the physical extents that are backing those blocks can actually be repurposed to do something better, something more useful. And so we have a new primitive in this API set, which will actually convey block liveness information from the hypervisor to the disk array, such that it can reclaim the blocks in red. Now, if it was just this problem was limited to deleting objects, I would not have considered addressing it at this priority. But as you can see, many technologies that enable dynamism and which you like to use create this problem on the fly. And so it is much more prevalent and much more important to address it. And then the obvious thing to say here is with this technology in place, the ability to reclaim previously deleted blocks, you could see that if you have a VM workload, a whole bunch of VMs which are occupying some storage footprint on your disk array, no matter the number of operations you do, you move them around, you power them on, power them off, you create and delete swap files, create and delete snapshots for backup purposes, you'll see that the overall storage footprint stays contained, which is very important when we are talking about thousands of VMs per data store. And then, in spite of containing the storage footprint, you do need that sense of security. And so what we are doing in terms of improving the operational capability of thin provisioning is typically vendors have warnings set for when the amount of physical space usage on a thin provision data store exceeds some number. And so out here on the right top, I'm showing a small clipping from the Dell EcoLogic UI, where it's kind of hard to read, but there's a warning in red which says we've exceeded the physical space, the, so to speak, quota configured for this volume. In this case, the volume is 10 gigabytes thin provisioned, and the warning threshold was set to 5 gigabytes. We are using a little more than 5. We are using 5.3 gigabytes. And so that's what the storage administrator sees, but the virtual machine administrator, the user of that LAN, doesn't realize there's a problem until he or she gets a phone call. And so what we've done with the clipping in the middle is you'll see that warning in the vSphere UI. And obviously, if you happen to use the vSphere SDK, then you can obviously get access to this warning too. And then you can react to it. Things like storage vMotion now make it possible for you to mitigate space usage from that LAN, move some VMs around. And then things like space reclamation will actually make sure that what you moved out is now actually unmapped from the source LAN. And then as you can see in the screenshot from at the bottom, again, Dell EcoLogic, the warning has disappeared, and free space now shows as 465 megabytes. And so the 5 gig VM has just moved to someplace else. There's a question here?
Is automatic LUN growth part of this as well?
Automatic LUN growth as in hardware LUN growth? Oh yes, of course. And so you can grow the LUN, you can extend the VMFS volume, and all this keeps working. There's obviously the final eventuality, which no one wants to go to, is you really run out of space. And at this point, presently what will happen is it is quite catastrophic if you are running a virtual machine workload, because a single LAN going away takes all the virtual machines running on that LAN offline. And so that is yet another argument to not do a really densely packed LAN or a data store. And so we are going to address that by taking offline or pausing only the VMs that actually cause the problem to happen, whereas other VMs who are just simply doing reads or rewrites just continue to go on. And so let me put it all together, everything that we just said. And so I'm showing a bunch of VMs running on the hypervisor accessing a thin provision LAN. Today, when you're close to running out of space, you don't get a warning. But in the future, you would, which will allow you to take some mitigation steps, such as storage vMotion. And then in spite of all your best efforts, if things really go south, then today there is no way to do isolation when it comes to storage. And so the LAN, of course, goes offline. This is standard practice among most storage partners. And that will take all the VMs that are running off of that LAN offline. That took more time to do than writing the code, actually. But in the future, it's only the VM that is affected, the one I'm showing in orange, that is going to be paused. It won't be offline, it's going to be paused. And you'll see a dialog box in the UI, which will ask you to provision some more space and then click OK. Of course, you can cancel, at which point we'll destroy that VM. So either outcome is OK. But then you'll notice that the other 3 VMs continue to run. So, the flavor of this talk has been a lot of data path changes. We've seen performance scalability changes. We've seen capacity optimization, some OpEx related changes. So the last thing I'd like to discuss in terms of the future is this other API set, which is not data path. It's mostly oriented towards improving manageability of virtual machines, which are running on really sophisticated storage. SAN or NAS storage. And we're going to call it tentatively vStorage APIs for storage awareness. And the problem we are trying to solve here is the consequences of doing a virtual machine action on physical storage is usually not known. And it's also not accounted for. And we already saw the space reclamation part. That is one example. The consequences of moving a virtual machine from one volume to another causes actual physical space to bloat up, but that is not within any obvious calculations that you see in some UI. And so that causes some manageability problems. There's performance-related consequences. If, for example, a vSphere administrator can choose to do storage vMotion, or he or she can choose to provision a virtual machine to a certain data store, knowing that that data store is relatively free or underutilized when it goes to performance. But then in the back, it might just so happen that the actual physical storage extents for that data store might be really highly utilized, or that data store might actually be close to running out of physical space backing the thin provision data store. And so we'd like to marry the two things, what happens at the virtualization layer and what actually happens at the storage layer. And the way we'd like to do it is we want to import a few properties and functions of storage. We want to model it as part of the virtual machine object model that you are probably familiar with. That's how the VMware SDK works. And so once you get to model it, all the workflows that relate to VMs, be it storage vMotion decision making. If you happen to go to the storage DRS talk, there's fancy algorithms now being invented to figure out where you should place your virtual machine. And so those algorithms can now take into account actual physical storage properties to make sure that the decision that we've arrived on based on just virtual properties, everything that the hypervisor sees, is a decision that is also okay with the underlying storage. So that's where we are going with here. One maybe obvious question that might arise is, are we going to take over physical storage management? And the answer is no. That's someone else's problem. What we want to do is make sure that virtual machines don't cause crazy consequences for the physical storage guys. And that's where we leave it at. Unfortunately, because these APIs relate to storage properties and some storage functions and modeling them, there is no good way to actually present it in the time we have left. But we'll leave you with some conclusions, some takeaways, and then we'll be extremely happy to answer your questions. We've designed it such that we have enough time for questions. But the takeaways here are kind of clear. One is vStorage API is an unprecedented effort. It's going to be multi-release. It's not this one thing that we do in a release and forget about it. And so you'll keep on seeing new changes. We just shared 2 of those changes with you. There'll be more in the future. If you are a customer or an IT manager, then it is a good time to actually start thinking about how this will change the way you make decisions around using storage, or how you use functions built on top of storage. And finally, if you happen to talk to your storage vendors or our storage partners, you can have a conversation about how various differentiating items that they put into their hardware can then be hooked up with vStorage APIs so that the virtualization layer can use it. That's all we had. We'd welcome some questions, and if you can step up to the mic, since it's recorded.
Can you talk about the NFS, the plans for NFS support? And I guess I'm just talking about it sounds very scuzzy and block-oriented, but a lot of what you're doing seems like it should actually be easier in NFS because you already have files. So.
Yeah, so that's a good point. So one thing about NFS, the vStorage API offloads that Lucas discussed, the VAI offloads, so to speak, they are already being worked on in the NFS realm. And so, the goal of the VAI presentation was at least to make you familiar with what happened in vSphere 4.1, but you can expect similar things to come out for NFS in a future product. The second thing is various things, like you said, are not problems in NFS. For example, if you delete a file on NFS, then the delete operation goes to the filer, which means it knows what blocks to actually reclaim and so on. So that becomes a non-issue. There are, obviously, when you go to talk about management APIs, then obviously NFS is relevant as much as block. And so, for example, vStorage API for storage awareness is modeling NAS storage and SAN storage right out of the gate. We couldn't do that for VAI because the NAS vendors were, in terms of implementing it, there was some disparity between how fast it could be done. You can imagine why it is, because the NAS vendor would actually have to do offloads on a per file basis, which is much more complicated than giving a SAN guy just little blocks to clone or zero. Another question?
So The next step is solving the free block space leakage on, the VMFS. But what about inside the client OSs?
Very relevant question, and we are working on it. Unfortunately, too early to share, but yes, it's on the top of our minds. Question here.
Could you talk a little bit about the RDM, support for RDM?
Oh, right, support for RDM. So cloning, zeroing, those primitives are actually supported for RDMs. So if you storage vMotion, storage vMotion RDM to a virtual disk or vice versa, all that will just work.
What about disk locking?
Disk locking doesn't apply to RDMs because it's not a VMFS volume.
And for the future, what's your recommendation for RDM? Should we get away from the RDM or still going on RDM in our environment?
There's only two reasons to use RDMs. One is if you are using MSCS, and the other one if your application requires a disk size which is so big that maybe you'll just end up storing one disk on the VMFS volume. And I'm sorry, there is a third reason, which is if you are running some SAN-aware applications which do some vendor-specific commands on the wire. As you can see with VAI, we have the storage partners and VMware, we have a shared vision, is that we'd like to give the virtual disk should be represented on physical storage as a first-class entity. And when that happens, it's going to take some time, but then, RDMs just go away.
Mm-hmm. Yeah, our message has been that you use RDM sparingly in the specific use cases that Satya mentioned. And you know that every time you assign an RDM, you burn one LUN ID. Right? Very fast, yes.
Question?
Yeah, so just following up on the dead block reclaiming inside of clients. If a lot of client OSs are coming out with support for write same, do you know if any of the virtual SCSI adapters will pass write same back through the layer?
That's the direction. Right. So we'll, as part of the vStorage API for thin provisioning thing, this has been in the works for a while, at least with storage partners. And so we've had tremendous traction at T10, and again, thanks to our storage partners. And so there are some commands, write same with unmap, the unmap CDB. There's a bunch of error codes that were accepted for the out-of-space condition. And so, yes, you can imagine that the virtual SCSI layer will also turn around to supporting them whenever it's necessary, whenever we get around to actually addressing the guest space reclamation problem.
Okay. So that there's a requirement for the guest space escalation, the VMFS support for write same and so on, the thin provisioning stuff that you were talking about, to be implemented first?
There is, for VMFS implementation, there's a requirement that the storage hardware vendor implement unmap. Right. There are a few reasons why we chose unmap as opposed to write same with unmap, but yeah.
Okay. Thanks.
Sure. Just one more question.
On the NFS front, the vStorage APIs, are they only available to your storage partners, or are they also available to regular clients?
There's the program has opened up to apparently the tap select storage partners. Is that right?
Tap select and above,
right.
Raju.
Right. So yes, large number of storage partners.
Okay, so
now
it's only storage partners.
Right. And thanks for bringing it up, because one other thing is, depending on the vStorage API program that you are interested in, it's a different kind of storage partner that you are, right? So if you are talking about vStorage APIs for data protection, it's usually ISVs who do backup and DR and so on. But if you're talking about VAI, it's usually storage hardware vendors, OEMs.
The reason I ask is, obviously with file systems like BTRFS out there, people are very interested in doing snapshots and whatnot at that level without having to engage, like a NetApp or whatever.
Right.
And if we were able to implement, some sort of tie into VMware, that'd be very, very helpful
I
for
see.
us.
That is, yes, I think that's a valid use case. It's actually quite hot too, is all I'll say.
Thank you.
By the way, in case you guys, it's too far, the mic is too far, but feel free to ask questions if you want, and I'll repeat them.
I have a question on slide 10, where you were going through some of the details of each of the three primitives. Two of the primitives you listed had a default value. assigned to them, did that imply that the user could adjust that for performance adjustment, or what did you mean by putting a default value there?
I see. Right. So I guess I'll take it. I guess you're referring to the default value of 4 MB as being the transfer size when you're attempting a copy offload, 1 MB when you're attempting a zero offload. They are adjustable. They show up in the advanced config list in our UI. We recommend not to adjust them because we go through a lot of testing, and it's not just correctness issues, but also about fairness issues. Is these VMs are issuing offloads, and all these things have to be fair to other virtual machines that are also sharing the same LAN. And so we try to take resource management, error handling conditions in mind. For example, if you try to offload more, let's say 16 megabytes a time, and that one command errors out, you lost much more than a 4 MB command erroring out, and so on. But that said, every generation of ESX will tweak that value to be relevant to the kind of hardware that ships in that generation. Another question.
Is there any increased possibility of data corruption? I mean, if an offload command fails, do you have some ghost file left somewhere, or how do you clean that up or deal with that?
I see. So 2 answers to that question. As you saw, the offload commands are just transacting in terms of blocks, something that is very familiar to SCSI implementers. The cluster-wide scenarios that lead to data corruption, such as a rogue file being left behind, etc., or locking a file such that while you are writing to that file through offloads or any such means, all that is VMware's responsibility. All that is VMFS's responsibility, and we have proven algorithms already and locking techniques to do that. The other answer to your question is we have a certification suite in place, such that storage vendors can self-certify their firmware. So between the two, we should be covered. Question there?
Will storage API work in opposite direction? Because I can see in the future, you choose a one.
Right.
Instead of only choosing side, you might choose a low, or medium, or fast one. But the same admin may hear the discipline name and turn fast on to the slow one.
Oh, right. So very good question. And so that's, in fact, where vStorage API for storage awareness comes in, is no matter what the SAN admin would do, we would mine those properties up, and we hopefully keep it reasonably up to date. So, yeah.
You realize you're killing the Java storage admin.
Actually, I like to argue no, because what we are trying to do is, make the vSphere admin and the storage admin fight less. And so...
Because the storage admin gets fired later. Gets to do whatever they want.
No, the storage admin should do whatever they want. In fact, with the kind of storage that we run on, I don't think the vSphere admin wants to. And the number of VMs that the vSphere admin is managing, I think the guy wouldn't have a life if he goes into storage. Like I said, we just need to tie in the problems that happen because the vSphere admin is using storage in a way that the storage admin didn't even architect it for. There is no other system in the world which does things like storage vMotion and does it at the speed that you just don't even think about it twice. Well, unfortunately, it has consequences on how the storage admin thought storage would be used. So, of course, both will change over time. But while they are there, we want to make sure that all our automated algorithms are sane. They are not creating.
The reason I made that comment was because it looks like the long-term roadmap for this whole process is to the full integration of everything into vSphere.
Right, and
both sides, from your side as well as the storage.
As their side, right. And I'd like to again highlight one thing, which is there is the virtual machine object. We model it, we export it through our SDK, and this virtual machine object has a virtual disk object. Now it's being offloaded. And so a storage vendor or any other ISV who wants to actually do storage management software for virtual machines can just hook into the SDK and do exactly everything that vCenter would do. And so it's a two-way thing. You know, we are not taking away storage properties into our layer just to hide them from everyone else. And in fact, they'll be exported out with a value add, right? They'll be exported out in the context of a virtual disk or a virtual machine where it actually makes sense.
Think of this way, we want to enable you to do your job more efficient in that today, actually as of 2009, there are studies of 10.8 million virtual machines deployed. So by 2012, the projection is 58 million virtual machines. You know, that drives a lot of storage, right? So we do not want storage administration to be the bottleneck. So with all this vision of cloud computing, starting with the vSphere, with the vStorage API being the building blocks for the cloud computing, we enable the storage administrator to do work more efficient, much faster, because you need to scale from 10 million virtual machines to 58 million virtual machines. Imagine the task you need to manage that many virtual machines.
Yeah, but can you envision a point where a new NetApp comes in, all you have to do is cable it and put in the address of your vSphere server, and then you switch over and just do everything from there? I mean, that's what I'm seeing. That's what's coming.
As endpoint. Well, we'll see if we are allowed to do that. But yeah, that'd be nice. That'd be nirvana.
It seems like all the storage vendors are going that way too. They're all doing the plugins and stuff.
Right. I think everyone's realizing at the scale, for example, like Lucas said, 58 million virtual machines can't be managed with Excel spreadsheets. Mm-hmm. So, it's a question.
Some of the SAN vendors on the SAN level in provisioning are reclaiming zero blocks.
Right.
So they have that in the roadmap. How does your stuff work with that?
Good question. Again, to repeat, some of the SAN vendors are reclaiming zero blocks. If you happen to write zeros, they'll just store meta information instead of actually writing zeros. And so stuff works. In fact, what we are doing is, without vStorage APIs, the SAN vendor is going to just blindly reclaim those zero blocks. We like to claim that, well, we know the context that is actually trying to do the zeroing. Now, if the zeroing is actually for space allocation, you better do the zeroing. And when the zeroing is to actually unmap something, you can do unmap. And so there's vStorage API actually has two primitives, one to unmap, one to zero, so that the action is explicit. Now, of course, the SAN vendor is free to actually implement both things with the same technology, which is just to, not write the zeros, which is fine.
But you'll know that it's how thin provisioned it is, even if it's doing it itself.
Exactly. So that's where, again, storage awareness APIs will get us our, the space utilization information.
You mentioned API provision, but I had the impression that you use the T10, the draft T10 commands that
right.
Mac or, let's say.
Yes.
Is that true?
Yes, so it's funny how these things go. In fact, I'm extremely pleased at how fast T10 is moving nowadays. But VMware, APIs for thin provisioning, we drafted them many months, actually more than a year ago. At which point T10 didn't have standard commands. But then over some time, we got standardization for, and by we I mean storage partners and VMware, we got to standardize every command that we are using for VAI and every command that we are going to use for thin provisioning. Nonetheless, we are going to keep the vStorage API program around because regardless of whether you are doing T10 commands or vendor-specific commands, we have this program where we say, these are the commands you would implement, and the following are the operational characteristics. So, for example, to vendors, we specify at what concurrency levels you should expect clone offloads. How many thousands per second or how many hundreds per second, and what are the locking characteristics that is expected, and so on and so forth. Whether the storage vendor should expect writes to come in while a clone is going on to a block, and so on and so forth. So there's, all that is covered, unsaid things from the standards are still covered through the vStorage API spec.
So somebody with all the T10 optional commands that say, that's what we discussed in the draft now, even without the API, there's a good chance that you will.
Yeah, there'll be a good chance. If someone did the T10 commands that we are after, there is a good chance it'll work. In fact, one of them worked when vSphere 4.1 was released. So, yeah.
One specific question. So what's the T10 command for the atomic
It's compare and write. I think it's 89H. Question?
Last one. Do you see things moving towards needing a more fundamentally distributed storage architecture anytime real soon? DNFS or something else? I mean,
Yeah, that's a great question. And Jay Jetkovich, who is our product manager, he covers it in his storage vision talk, which, by the way, clashes with this one. You made the right choice. But yes, we do see a shift from just monolithic storage system to some form of scale-out storage systems. It could still be in the form of still chassis that ship from storage vendors, but then they are smaller and you can add on as your requirements grow, as opposed to buying a fridge cabinet to start with. And then there's another shift, which is, many storage vendors make these appliances and they somehow cluster themselves together to do interesting things. I don't know what you were after with your question, but I see vStorage APIs as being relevant to both these classes, because after all, if you are not in VMware, if you are a storage vendor, then you want to implement various things that will differentiate your storage. And then it is vStorage API's goal to actually leverage the things that you just implemented for differentiation.
Yeah, I guess it was specifically some of the thin provisioning stuff you mentioned. I mean, that's something that historically would be in a NAS or something, or a vPlex or whatever.
Right.
And it sort of looks like you guys are moving that in-house so we can scale out.
Oh, well, right, but then more importantly, we have built-in algorithms which are now going to use the thin provisioning functionality, which, like you said, vPlex or some NAS device implemented. So we are, the storage array vendor's functionality is not subverted. It's, in fact, now it's more usable.
All right, thank you.
All right, thanks for coming, guys.